Martha, thanks for joining us today on Approximately Correct.
Thanks for having me.
It's great to have you here.
I wanted to start with a pretty general question, which is just, how did you get into research?
I suppose a lot of people, I did research in my undergrad. There's a thing called an NSERC USRA. That's an undergrad summer research program. So me and my friend saw a sign in the department and thought, okay, we'll go check out what this is. And then we sort of scrolled through different professors in the department. I found one that looked like he was really nice, which was Michael Bowling. I went and knocked on his door, and he was willing to have me as a summer student, and that's how it all started. So, each summer you learn a little bit about what's it like to go into research. I sort of got set up for how do I get into grad school? What do I really want to do in grad school? And then from there in grad studies, I mostly worked actually on unsupervised learning and semi-supervised learning, which is, you can think of as sort of like representation learning. You want to extract patterns from data. But the lab that I sat in was the reinforced learning and AI lab. So I was sort of surrounded by people doing reinforcement learning. And so I sort of slowly started gravitating towards reinforced learning, which I think is a really interesting research area. And so by the time I was done my PhD, that was really what my focus was.
And that's interesting and a good lesson. So you just went and knocked on Mike's door.
Right. Yeah.
And were you nervous to do that?
I wish I could remember. Probably. I'm sure I was.
Yeah.
Was he nice?
He is very nice. He was nice and is very nice.
Continues to be nice.
Yeah.
That's good. That's great. That's a good story. Also, Mike was our very first guest on Approximately Correct. So.
And he was nice then too.
Yes, he continues to be nice.
Yeah, right.
So then you did an undergrad project, you did your master's, PhD, and then how did you know what you wanted to do next?
I suppose actually at the end of my PhD, I applied for professor positions. And in order to do that, you have to write a research statement. And it was the first time I really sat down and thought, what is my research vision? Like, what do I think is really important? And there I sort of had a history of representation learning, which is how do you take data and convert it into a form that makes it more amenable to something else learning on top of it. For example, making predictions on top of it, or having a reinforced learning policy, which is a way of behaving, make decisions in the real world. So for me, I sort of brought that background with me and also wanted to know how do you make that happen continually. So my focus has always been, since becoming focused on reinforced learning, how do you have an agent learning in the real world continually from a stream of interaction? So I after writing that research statement, I realized I really truly believe this is something we must have if we're going to bring learning decision-making strategies into the real world, like a combination of representation learning and continual reinforcement learning. So, and since then, that's what I've been working on.
That's something I've definitely heard, that like sitting down and writing about your thoughts and your ideas helps to make them more clear and also can help you see your path.
Yeah,
it's really cool.
absolutely.
Yeah.
It sounds intimidating to kind of have to sit down and really focus on what really you're focused on.
Yeah, it's true. It's intimidating because you start off by not having any idea, but it's also illuminating. By the end, it was a good exercise. I mean, there was maybe like 4 discarded versions of it, but
Oh yeah, so it wasn't first draft.
No, first draft was not the final draft.
And we sort of like complain about writing grants, but I think the same is true for grant writing. That like sitting down and writing out what your plan is, you will throw away multiple versions, and you'll see that what you had originally thought of is actually not the right thing to do, but it was, on the path to figuring out that right thing.
100%. I think grants are great for focusing our research vision.
Also exhausting, but great.
Yes, I don't like doing it, but when I'm forced to do it, it's good.
It's always, yeah.
Yeah, well, if it was easy, it wouldn't be helpful.
Yeah.
Right.
You talked about that interest in agents that are working in the real world, and that's something we really want to talk about today. So what is it about that idea that you find really draws you?
Well, I guess if we want to have support for how people, run the world, the way that we automate our systems, the way that we make predictions ourselves, it's important to have machine learning. I think things that actually take data and convert that into predictions or also recommendations, and then in some cases, direct automation. I see all of those as different ways to support our own decision making. So to do that step, though, like how do we go from data to automation, for example, we need to have agents that are in the real world interacting with data, also sometimes interacting with people who are messy. And that's a much harder problem than, I have a data set and I'm trying to decide, is there cats or not cats in this image? So sort of shifting to that more realistic, messy setting is how we're actually going to have machine learning have impact.
As soon as you introduce people, everything seems to get messy.
Yeah, that's people. But I guess also even just messy data, like streaming data, there's always going to be some missing data. Obviously, automation is going to be harder than prediction because you have to think about how do you make sure it's safe? How do you actually ensure you also have people having oversight on top of that? if you have prediction systems, it's a little easier to give those predictions to people and allow them to make decisions after. So there is sort of an interesting question of how do you have machine learning systems that are constantly making predictions that are useful to people? And then there's a much bigger jump to, and then how do we actually turn some of that into direct automation?
And recently you've made a big step towards RL in the real world with a startup. So can you tell us a little bit about RL Core and how that came to be?
Sure, yeah. So RL Core is all about using reinforcement learning for optimizing operation of water treatment, but maybe more generally for industrial control. So I'll tell you where it started. It actually started as a research project at the University of Alberta. An engineering company approached us and said, hey, we really want to understand how can we use this machine learning thing to improve operation of water treatment facilities. So with them, we built a pilot plant inside the larger actual water treatment plant at Drayton Valley, Alberta, and we ran reinforcement learning experiments on that. So the water treatment process is actually quite simple. Water comes in from the river, goes into a big tank. Water is mixed in that tank with chemicals. That water then gets pushed through a filter that's kind of like a little sieve. The chemicals help things clump together so that it's easier for the sieve to drain, to filter those things out. And then periodically, as that sieve gets kind of clogged up, water gets pushed back the other direction in order to blow off all that gunk. That gets drained, and then you go back into producing water. So, but along those steps, there's actually a lot of really interesting control questions. You know, how should you be dosing chemical? How fast should you be mixing? Is there different patterns you could use for mixing? How frequently should you do this backwash? How long should it be? So there's all these different questions. And almost immediately we saw that reinforcement learning could be great for this. So one is that a lot of these set points or these choices are very static. Engineers do some testing when they commission the system, and then they just set it, and it's generally not changed again. But that's not particularly effective because the system changes, water quality changes, and it would be a lot better to continually adapt those things. So you can't have people constantly adapting those things using sensors, but you can have a machine doing it. And then it's also great for reinforcement learning because there's actually a pretty broad range of settings that work okay, maybe a little suboptimally, but your reinforcement learning agent can actually try lots of stuff on these systems without breaking them and without really doing a terrible job. So it's a great place for something to start off with an okay choice that engineers made, and then start to try to test around that and slowly start to improve the performance of the system. Again, without breaking anything, it's sort of in a safe kind of a way. So we did some work at the university. We had good progress. We saw that this was a great choice for reinforcement learning. And then to really bring into the real world, it was very natural that the next step should be a company that has a dedicated team of engineers, really turns that into a product, asks how do we get people to start using this in the real world.
Okay. And my understanding is when you're talking about water treatment, I mean, it's one of those things where the scenario is changing quite rapidly. Like, you know, if it rains, it's different. If it's a different time of year. So
yeah, absolutely. There's sort of things that change contextually based on the year. And then there's other things that actually just drift over time. Like the filter, this sieve is constantly getting worse and worse over time. It doesn't ever go back to its original conditions when you first bought it. So there's just sort of a constant drift of the system in terms of the actual degradation of the system. And then, like you said, sort of seasonal changes or weekly changes if it's raining or not raining. So it's a very variable system.
Okay.
How much better was it after you tried reinforcement learning in this?
Right now, we are started getting actual specific numbers. So at the university, we saw we could make some improvements on this pilot system that we had, but now we're actually getting some numbers. One example is we changed just one simple thing, which is when you do this backwashing, there's a speed with which you send the water back through. So the flow rate, you can make it like higher or lower. And we got our reinforcement learning agent to try to start learning what would be the right flow rate to send through for backwashing. And there we managed to get a 20% improvement in the permeability of the filter on whatever the default strategy is. And of course, the defaults are good. Engineers sat down and figured out what's a good flow rate. So this was sort of on top of what was already an okay choice.
So yeah, it's kind of improving what we already were doing.
Yeah, usually these, the systems are running suboptimally, but acceptably. There's a reason they aren't changing them. It's okay, but we could be doing a lot better. So at least 20% in this case. I'm sure for other things we can actually save quite a bit more. For example, for chemicals, there's sort of a tendency to go a little higher. And also it's hard to constantly change the chemicals as well. People have to make do a little jar test to decide what the chemical should be, but absolutely those could be changing throughout the day as water conditions change. So I think for things like chemicals, we might actually be able to save more.
And what's a jar test? Sorry.
Yeah, so let me tell you what that is. So right now, the way that our system works is most things are static, like how often you backwash, what the flow rate is, and so on. But there is one thing that is actually changed daily, and that's by the operators themselves. So you can think of them as the control strategy.
All right.
And they'll take samples of water, they'll put them in different jars, and they'll just put different levels of chemical in each jar. And then based on the properties of the resulting water, they'll decide, okay, I'm going to use the chemical dosing rate that's in jar 3, for example. So like very minimal dosing to much higher dosing. And they're essentially little chemists trying to figure out what's the right dosing rate.
Sounds like a painstaking process.
It's somewhat time consuming, and I think they would like to do it more frequently, actually. So one of the issues for them too is they do it once a day, usually in the morning, and then they sort of just have to pick that value. And it would be nice to be able to adjust it throughout the day sometimes. But yeah, they don't have time. Operators are busy people.
Yeah, there's a lot going on.
They have a lot of maintenance to do, a lot of oversight of the whole plant. It would be absolutely reasonable to take this off their hands.
So is that something you're thinking about? Like, could we actually automate the jar test?
Oh, we could absolutely automate dosing because right now you need to add a couple of sensors. That's what we're doing right now. Actually, the way we're starting is by working with the operators. The operators tell us here's what we would dose for the day, and then we just adjust around that to see if we can get improvements just for within that day. Ultimately, though, it would make a lot of sense just to take that off the operator's hands and dose directly, maybe with some input from the operators around ultimately what their goals are. Their ultimate goal is we want the water quality at the end to have these properties. We want this level of light to transmit through that water, and they know what that number is. Sometimes it might change, like let's say their KPIs change, their goals for the water change. That's the level with which people should be having input, and the system underneath should be changing dosing and so on to achieve what people want out of the system.
You brought up like the amount of light. Is that a measurement?
Yeah, so there's a sensor. I like you're asking very specific questions about this, but there's a measurement that we take called the UVT. Ultraviolet transmissivity is probably what it is. And so light shines through the water, and based on how much light is going through the water, like how much it transmits through, tells you that there's not too much stuff in the water. So if you had very dirty water with lots of particles, light's going to hit those particles and it won't come out the other end, right? Like it's going to be stopped. So there's not a lot of transmissivity. Whereas if you have very, very clean water, the light's going to be able to pass through the water easily. So they'll have conditions on what the transmissivity of the water should be at the end. For example, it should be at least 90% and should have other properties like the pH shouldn't be too off of neutral, things like that.
Oh, no. Okay. Yeah, I had no idea that that's one of the measurements to tell how good a job the treatment plant is doing.
Yeah, that's one of their key criteria.
So when you kind of approach this problem, what were some of the challenges that you knew you'd have to solve?
Yeah, I mean, I guess for me, there's 2 key challenges. One is, of course, on the technology side, and then the other one is on the adoption side. Mm-hmm. So we always knew that the adoption side was going to be the hardest. We believe our technology should work, right? Reinforced learning should work for these problems. I'm very passionate about that. And then the next step is to convince other people that they should use this technology. So for us, it's always going to be the adoption question. Yeah. It's the hardest question. And then for the technology side, though, we hadn't actually created reinforced learning agents that were going to continually changing backwashing, continually changing dosing. So it is sort of an applied research question right now. No one, as far as we know, has used reinforcement learning for these systems. If you're the first to something, we're going to run into some research challenges. We're not sort of just taking off-the-shelf machine learning, or let's say like large language models, and applying to this problem. We're designing reinforced learning methods from scratch for this problem specifically. So yeah, those are sort of our 2 key things that I'm always thinking about. How do we make sure we have robust, good solutions using reinforcement learning? And then how do we actually incorporate them into existing systems that are amenable to operators, show them the things that they want to know so that they're happy to adopt it?
Okay.
So what are the big research questions that come up when you try to launch RL into the real world?
For me, the main research questions are, I'll just say a little bit about how our pipeline works. Okay. What we would like to do is use historical data. Mm-hmm. So these plants do actually store a lot of data. They already have interesting sensors in their plants. As much as possible, we want to leverage that historical data to pre-train or start or initialize our reinforced learning agent. And then from there, it's going to learn in the real world in deployment. So the key research questions there are, how do we leverage this offline data most effectively? And then how do we sort of do that transition from this offline phase to the online phase and allow it to now start controlling the system? And in this online phase, we need to know, how do we specify guardrails in an effective way? How do we know we can reset the system back to a safe way? And then otherwise, how do we do exploration effectively on the system? Which means, how does the agent decide, this is the next thing I want to try because it'll get me information, or because I think it'll actually be much better than what we're currently doing? Right. So the questions are, how do we move from offline to the online setting? And then how do we gather new data that's useful? And then, of course, continually learn as we're actually controlling the system. So a key research question here is the off-policy learning question, actually, where this offline data is going to be typically from people. Like operators have been making decisions for years. It's logged in this data. It's different than what our policy will do once we deploy it on the system, but we still want to try to answer what if questions. So for example, let's say the operators chose to dose chemicals for the month of, let's say, July. Mm-hmm. We have all that historical data. We saw that they chose, a dosing rate of 10, and then they chose a dosing rate of 15, and then they chose a dosing rate of 10. We can sort of look at that and say, we might want to ask a question like, well, what if we had chosen a dosing rate instead of 20 or a lower dosing rate of 5? So as much as possible, the off-policy learning question is asking these kinds of what-if questions. I want to know what would have happened if I had done something differently, because that different thing might be better. So the off-policy question is, how do I take existing data and say, instead of behaving the way that, let's say, human operators did, if I behave differently, could I get better result? And so I need to answer these what-if questions.
And you can answer those what-if questions with existing historical data.
So there's going to be some limitations there. Yes, the answer is off-policy learning is designed all around take historical data, or at least data from a different way of behaving, and see if you can answer these what-if questions. And then now there's going to be limits. If your data has almost no variability, let's imagine operators never changed the dosing rate, they always set it to 10, they just didn't do jar tests at their site, then there's no real way to answer what would happen if I had done 20. That's just not really in the data. Right. But if you do actually have them doing some variability, you can't say on Tuesday when they set it to 10, what if I had set it to 20? Like, you just can't answer that question. We don't have parallel universes. But you can say on a different day that kind of looked like Tuesday, they did try 20. And now you might be able to infer what would have happened if on this Tuesday you had done 20, and then the next day you did 20, and so on. So in some sense, what you do is you look in the offline data, you take this previous data, and it's almost like you piece together different chunks of it to ask, if my policy I chose to dose lower for a week, lower than what the operators did, what might have been the outcome? And you can kind of infer that if there's that information elsewhere in the data.
So sorry, can you define for me what's a policy?
Yes. Okay. So a policy is, so in reinforced learning, the goal is to improve decision-making or automation. And so the policy is actually the thing making decisions. In this case, it would be, let's say, for deciding how to dose chemicals, the policy would say, given the current context of my facility, let's say the current water temperature, the current turbidity of the water, what time of year it is, condition on that information, what action should I take? And the actions would be the dosing rate itself. So the policy is the thing that says, what is this action that I should be taking to condition on this information about my facility.
Okay, so it's like the decision-making part.
Yeah, it's the decision-making part. It's the thing that decides how the system is going to behave.
And so what is off-policy then?
Okay, and so off-policy means that, I have what my current policy, what it wants to do. It wants to say, I think the best thing to do on this Tuesday is to take a dosing rate of 15, but my data says that a dosing rate of 10 was taken. So that's a different policy. It was, let's say, the operator's policy. And so that's off of or different from my policy. So I want to use information from running a different policy, again, operator policy in this case, to infer something about my policy, which is different than theirs.
Right. So it's off policy because the data was generated by, in this case, a person who has their own internal policy, but we're trying to learn a new policy. That's why it's off policy.
Exactly.
What would on policy be then?
And on policy would be that we could actually take our current policy, we would get to run it on the system, and we would get to see what is the actual outcome of my policy, right, which is obviously much more informative, because now I can say, I think taking a dosing rate of 15 here would be good, and then the next day taking 20, and then so on. And then I can actually check, was that or was that not good? So yeah, on policy data collection is very helpful. And in fact, that's what happens in the online phase. So I think it's so important to do the offline to online phase. Mm-hmm. It would be, I think there's some who would want to use reinforced learning just using historical data, and then they would deploy a static fixed policy. Mm-hmm. I think that is a mistake and also very difficult, just for what we've talked about. You can only infer so much from these offline data sets. Mm-hmm. Once you move to the online phase, it is actually more on policy, because the agent will say, I want to try this thing, and then it gets to try that thing and see the outcome of its own decisions. Slowly over time, it is, of course, accumulating all this new data as well. And that data itself becomes off policy because its policy changes. So we still need to have off policy learning in this online phase as well. But that data is much more useful and it lets the agent infer much more about these what if questions. So off policy learning is all about what if questions.
Okay. And what would be the reason that's, like you said, some people are more drawn towards just the offline parts? Why would that be the case?
Yeah, I'm not 100% sure why this has become a, you know what, actually, I do have an answer for you. Maybe I do know why. It feels safer to be able to say, I have a data set, I'm going to extract something from it. I'm going to learn my neural network. For us, policies are also neural networks. The neural network inputs state information or context information about the plant, and it spits out either directly an action or might split out a distribution over actions. Okay, so we're comfortable with learn function on data set, and then do some testing on that function. I could actually query with different values. I could get a sense of what do I think this policy does? And then I'm going to deploy that fixed thing. And I feel comfortable knowing I deployed something I understand. Whereas if you allow it to continue changing online, well, you can't perfectly track what it's going to do. It's going to incorporate new information. That neural network is going to change, and it's going to start taking different actions. And again, I can't monitor constantly. So it's essentially just going to go off and become its own thing. So I think there's a worry that it would, either become unstable, spiral out of control, start doing weird things. I think that's why. I disagree with that view, because I think if you take a static object, it'd be like training someone and then asking them to control the water plant and then never adjusting as things change in the water plant. It would be very brittle. You would be worried about someone just rote following a procedure, regardless of if that procedure makes sense anymore. So I believe it's much safer and better to have this policy adapting as things change in the plant, because if what it's doing is no longer working well, then it'll actually change what it's doing rather than just continuing to do that thing that's not working well.
Yeah, I guess they don't, when a new employee joins the water treatment plant, they don't train them and then just here's the keys. We're not checking up on you. That's
true too, but also as people, we're obviously constantly learning. So if I think this dosing rate should work and then it stops working, I'll probably assume something has changed about the plant, and I'll try a different dosing rate and then see, okay, now that's actually working better, which is what we want our policies, our agents to do as well.
And you did talk a little bit, like you used the word safer there, and I just want to check, because when you're talking about things like the cleanliness of water, that's obviously a pretty important outcome. So how do you approach a problem like that while keeping that safety in mind? Yeah,
so the beauty of these systems, a lot of these industrial automation systems, is their engineers know generally what are good safe guardrails. So for dosing rates, for example, we know that there's a range that is safe for not damaging the filters. We also know, for example, when you do this backwashing flow rate, it shouldn't be any lower than some flow rate, and it shouldn't be any higher than some flow rate. And anything in between is just going to make the backwash more or less effective, but it's not going to damage anything. Okay. So in some sense, these systems are sort of slow moving. We have guardrails, and we can always reset back to what the engineers thought was a good choice. So if for some reason our reinforcement agent started choosing a flow rate that wasn't cleaning those filters well enough, we can recognize that. That's being measured. It's called permeability. You can check how well the permeability is improved after a backwash. And we can have an automatic reset that says, okay, something's wrong with our agent. We wish that wasn't the case, but something's wrong with our agent. Let's reset back to the previous strategy, and it'll start cleaning that filter again properly. So there's sort of a recoverability for the systems that we're looking at that makes it more inherently safe. And engineers have designed these systems to be somewhat robust because people are operating them too, and we're not that great at operating things.
You make mistakes.
Yeah.
Everybody's got an off day.
Yeah. Now, of course, there's some industrial automation scenarios that are much higher risk. They could be unstable. They could be runaway. Those are not the problems I think we should start with. Like, there's a lot of these kinds of more stable problems where we can start asking, how do we use reinforced learning? That's where I want to start.
The word guardrail has just got me off on a bit of a tangent mentally here, because we talk about guardrails with language models a lot.
Okay.
And the set of guardrails are constantly changing, right? Because people are trying to get these models to do bad stuff, generate offensive things. But
so
I guess,
what would a guardrail be in that context?
There was an observation that the people generated by image generation AI were often white. Okay. And so they were like, okay, well, we better make some racially diverse people. And so the guardrail would actually be something like adding to the prompt, like racially diverse.
Right.
But then, of course, that's a problem, right? Because like racially diverse German World War II soldiers, I think was the example, right?
Yeah.
That's not they weren't racially diverse.
Right.
And so that sort of shows you another place where there has to be a different guardrail. So there's sort of a constant adjustment of guardrails, partially because the people interacting with this system are slightly adversarial.
Right.
Maybe overtly adversarial.
Right.
But that's different than your system, right?
Yeah, definitely the operators are collaborators. I kind of like to think that we're making an operator assistant where in the end, the operator is responsible for the whole plant. They want the whole plant to function well. And then here underneath, it's just the assistant is going to be doing things that a person doesn't want to do, like optimize this chemical dosing to meet this UBT. So I imagine there's a collaboration there, and the systems themselves are not adversarial. Like they're
like nature. I mean,
yeah,
nature is not adversarial. It's random. It can be extreme, but it's not specifically trying to wreck your filter.
yeah. I think that's true. And then I think the other important thing here is that we are in a feedback scenario. So if we have these guardrails, we have these ranges that are acceptable, but then it's not that we're doing arbitrary things inside those. We'll try something, and then if it's not working well, there's immediate feedback. The agency's, all right, that wasn't good, and it's going to go try other things. And if previously it was good, but now it's not good, again, it's going to get that feedback. So it's sort of constantly self-correcting, which I think is also a little different than large language models, which are not doing this online learning. They are sort of these big static objects.
Yeah, that's definitely true. Right. And they're not getting feedback about like, well, that was racist.
Yeah.
Until like much later, and the feedback comes from an engineer, and it's in the
that kind of built it in. Yeah.
Okay. I am very glad to hear that there's no adversarial engineers at the plant. Messing things up.
So are there scenarios where off-policy learning just like isn't going to work, or moving from off-policy to on-policy is not going to work?
Yeah, I mean, definitely there's always going to be limits. Like I said, you can't ask what-if questions if they're not really in the data. So actually, our data kind of looks like that. A lot of this historical data, we might even have 5 years of data, but I said the types of systems we're looking at are ones where the set points are not changed. So the engineers set these values on commissioning. Maybe a process engineer came in 3 years later and changed a couple of them. Maybe not. So like you have huge amounts of historical data, all with very little variability on these set points. So you really can't ask these what-if questions. So we actually do have the scenario where the offline data only plays a somewhat small role. We get to see something about how processes change, like we can sort of get a sense of how the system works. But then absolutely the most important part is the online phase. And the people we've worked with understand that. They see that, of course, the historical data doesn't allow us to ask what would have happened had we done X. So they let us go actually first do a manual gathering phase just so we can have a better understanding how the system works. They will go change values so that we can all get a better understanding of what happens. And then they're allowing us to do an automatic gathering phase afterwards, where our agent actually will run and will, again, stay within even more narrow guardrails, but it's going to do some more exploration inside those narrow guardrails. So off-policy learning, this offline phase, is going to be very limited if you have low data variability. And so that's why I kind of think of it as we're doing online learning and we also have some offline data.
Oh, that's cool. I didn't know you actually had a sort of an additional data collection phase where they allowed you to explore a little bit around what they had done previously.
Yeah, that's right. That's what we were doing.
So I'm also curious how you convinced this water treatment plant staff to let you do this.
Yeah, I mean, I think that in any industry, there's always the innovators who are just kind of interested to see what things they can do. And then there's everyone else. So like most people are sort of slightly more conservative. And then there's those few people who come out and say, yeah, I want to do this thing with you. Okay, so why is Drayton Valley this way? I'm not sure how ISL Engineering found. Okay, so ISL Engineering is the company that we're working with. They're the ones who set up their plant. Drayton Valley is kind of interesting. It's a small town of about 7,000 people, but they had this like big water innovation center that I think was built in collaboration with the government. They had like a terrible water treatment facility. Then with the government, they got some grants to build this much nicer ultrafiltration system. It's pretty unique in Alberta, actually. And so I think they sort of had a view that they should do innovation there at their water innovation center. So far, they've just been our partner. They've just in kind taken the time. We don't pay them anything. The operators are just kind enough to work with us on this. So how we convince them, I guess we would just like it to have innovative people to work with. And another group we're working with is EPCOR, Edmonton's Municipal Water and Wastewater group. And they also just seem like a very innovative company. They want to understand how could we use AI.
And maybe you're coming at it as like helping solve a problem or make their jobs easier, and maybe that's a somewhat easier sell.
Right. So there's the higher level organization, then there's the operators and process engineers themselves. Absolutely, those people, I believe anyway, operators know that they're indispensable. There is no replacing operators. They're constantly fixing broken things. I don't know if you guys know, but in these plants, it's constantly breaking.
Yeah.
Pumps break, valves break. They have to be there to pay attention.
Because they're on all the time. Like, I mean,
exactly.
Of course, yeah.
So all we can do is do like a little cherry on top. We can make things a little more efficient. Maybe we can alarm when things are like looking strange. So we are really just there to support their operation to make it better. And right now they have things that they know could be operated better, but they don't have the time for someone to sit there and carefully tune these set points. So they want that to be done. They want their system to be more efficient, but they don't have the time to do it.
The Drayton Valley, did those people actually approach you, or sort of? How did you...
No, actually, ISL Engineering is the ones who approached the university. Yeah.
Oh, and then the university said, like, here's some people over here.
Actually, I think they might have approached David Wishart first. I don't know the full history of this, but eventually they got directed to Chaba. So Chaba's actually the person who started working on this. Oh, okay. And then Chaba roped me into this. Yeah, cool. And it's great. Yeah, it's great that he did.
That's a good U of A story.
Yeah, absolutely. And you did talk about it a little bit about that, there was technical challenges and then there's adoption challenges. And it sounds like you had a really good experience with people wishing to innovate here. But I mean, for some other people who might be, either industrial control or other industries who are sort of on the fence or a little wary, like what would you tell them?
All right. So other groups, let's say.
Yeah. Who are like thinking about it, but maybe aren't quite sure if they are.
I mean, our current strategy is whenever you have those groups who are less sure, you sort of start with the innovators and then you make demonstrations and you show what you can do. And then that way, when you come and talk to those other people, you have very concrete evidence of what you can do. And that concrete evidence is hopefully going to help. But I'll tell you in 8 months.
Okay.
However long it is until we reach those people who are a little more conservative.
Did you just promise to come back on the podcast?
I think that's a legally binding promise. So I know, obviously, like this is a process that you're still working in, but has there been anything that's surprised you so far as you're going through?
In the startup world or maybe specifically industrial automation?
No, but anything in the kind of the whole journey that you guys...
I guess lots of things have been surprising. Maybe some things that have been surprising is how receptive operators have been to like using machine learning incorporated into their system. I was expecting a lot more conservatism, like don't touch our thing, AI is a terminator, et cetera, et cetera. But they sort of understand that having... like they do some guess and testing on a system. Like that's like a normal thing for them. So when we say we would like our agent to try these things, they just seem quite comfortable with it. And they seem confident in their ability to also maintain the plant. So I've sort of been surprised at how receptive operators are. They're of course still cautious. They're not like just start running stuff on our system willy-nilly. But they've been more receptive than I expected. I guess I've been surprised at how helpful everyone is in the business world. Yeah, how much they're willing to answer my cold call emails for suggestions. I email everyone and try to get advice from everyone. So I've gotten a surprising number of people saying, okay, sure, I'll chat with you. Yeah, maybe those are the most surprising.
Well, I'll flip it around then, because it sounds like you got a lot of advice from people. If you were to give advice to somebody who's planning their own startup, what would you say?
Okay. One thing for sure is get co-founders. Doing this alone would be awful. So I have 2 co-founders, Adam White and Alden Christensen. And particularly Alden has a very different skill set from mine. Like I'm on the technical side, the research side, and Alden has been a project manager for years. He was with Google for many years for doing their like big infrastructure projects. Yep. So he has a lot of wealth of understanding of like how do you get good culture, how do you manage people, how do you manage large projects. And it has been immensely helpful having someone who knows how to do all that stuff. And of course, just otherwise having other people to talk to and make good decisions is super important rather than doing that all by yourself. And otherwise, I would encourage people to not be squeamish about asking everyone for help. Just ask. They'll say no, or they'll say yes begrudgingly, but then you got that help. So that was good. And
you'd be surprised, man. Some people want to help you.
Yeah, exactly.
And if you don't ask, they won't. But if you ask, sometimes
exactly. Yeah. So you just have to be unembarrassed and ask. And then, I think the most important thing we have done is hired very carefully. And I think everyone will tell you hiring is the most important thing, but hiring is the most important thing. Our team is great. It has made everything work very smoothly. Okay, and then otherwise, the piece of advice I've been told over and over again is make sure that you are working on an actual product. Like don't just hypothetically create reinforcement learning software that you hope someone will buy. You need to go and decide this is the thing we're doing. We're going to actually work with someone on this product, and you know that someone wants that product.
Right.
Yeah. Right. Solve a problem.
Solve a problem.
Somebody actually has. Not the problem that you wish someone had.
That's right. Don't just make someone. People definitely want this reinforcement learning software. Right? Is not going to work for you.
Right.
Yeah. That seems like such a simple thing, but I could definitely see how it's a very easy trap to fall in.
I've talked to multiple companies that have fallen into this trap and now have failed.
Yeah.
Specifically not specifically reinforced learning. Actually, one was reinforced learning, one was not.
Yeah.
And if somebody wanted to learn more about RL Core and what you're doing, what would be the best way for them to do that?
We do have a website that is in progress and needs more information on it. So slowly over time, our website will be a great place to learn more about it. Otherwise, we are also hiring, so they should apply. We'll probably respond to them. I don't have a better answer than that. So talk to me in 8 months.
Right. Again,
we'll have all that information online. We'll have great videos about all the things we're doing. Yeah, we're still sort of in the early phase. We were just created in October.
Right.
And since then, we've been really focused on pilots. So like proving out the technology, creating the technology, getting the demos, like numbers, like we have 20% improvement. And so some of that is slowly filtering its way onto the website, but we're sort of focused.
Filtering its way onto the website. 20%.
Only the best stuff ends up on the website.
Yeah. Thanks so much for joining us today, Martha.
Thank you for having me.
Really, really interesting to learn more about what you're doing.